Hello everyone, welcome to Tech with Machines. After distributed locking, let's talk about leader election in distributed systems and why do we need even a leader. Imagine you have 5 servers running your system. They all look identical, they all can process requests, but one of them must coordinate everything. Now imagine that server suddenly crashes. Who takes over? And more importantly, how do the remaining servers decide without a boss who becomes the new leader? Today, we are going to understand how distributed systems elect a leader, from simple algorithms to how Kafka or Elasticsearch actually do it in production. Now, let's talk about a core problem. In distributed systems, we don't have a central authority. We have multiple nodes working together, but some responsibilities can't be done by everyone at the same time. For example, write coordination, managing metadata, scheduling jobs, handling replication. If multiple nodes try to do these simultaneously, we will get chaos. So the core question becomes, how do we safely pick exactly one node to lead? Why do we even need a leader? Many real-world systems depend on a leader. Kafka has a controller node, Elastic as well as Solar has a master node, Kubernetes relies on etcd leadership, databases as well have a primary node. The leader typically will coordinate cluster state, will schedule tasks, will ensure there is consistency as well as control configuration updates. At the same point of time, also manage replication. Without leadership, distributed systems become unpredictable. Now, what happens without a leader? Let's say 2 nodes both believe they are the leader. Now, both accept writes, schedule the same job, update the metadata. This results in duplicate processing, a complete chaos with conflicting writes as well as the corrupted data. This situation is called split brain, and preventing split brain is one of the core goals of LeaderElection. Now let's talk about a naive approach of electing a leader. Let's say the simplest idea is each node generates a random number, highest number wins. Sounds simple? But what if 2 nodes generate the same number? Network partitions happen, or nodes don't see each other. There is no guarantee of agreement. Random selection without coordination doesn't work reliably. So let's talk about another algorithm called Bully algorithm. So we will improve the previous approach. Bully algorithm works like this. Each node has a unique ID. The highest ID always becomes the leader. If a node detects that the leader has failed, it sends selection messages to nodes with higher IDs. If none responds, it declares itself the leader. This works better than randomness, but it still assumes reliable communication. So there are still problems with Bully algorithm. It will generate too many election messages. It will assume that nodes can always reach higher IDs. It doesn't handle network partitions well and also can't scale gracefully. In modern distributed systems, we need something stronger. That is why enters coordination services. Instead of implementing election logic ourselves, modern systems use coordination services. You would have heard about ZooKeeper, etcd, console. These systems provide strong consistency, ephemeral nodes, watches, as well as the quorum-based decisions. They are designed specifically for coordination problems. Now, ZooKeeper LeaderElection is one of the coordination services. Each node creates ephemeral sequential node. ZooKeeper assigns increasing sequence numbers. The node with the smallest sequence number will become a leader. If the leader crashes, its ephemeral node disappears automatically. Then the next smallest sequence number will become a leader. This is clean, deterministic, and reliable. Now, why do ephemeral nodes matter? Ephemeral is equal to auto-deleted, deleted on disconnect, which means the temporary node. If the node disconnects, even due to network failure, its entry disappears. This will prevent ghost leaders. Without ephemeral nodes, a crashed leader might still appear alive in the system, and that would be dangerous. Now, what is the modern take? Today, most modern systems use a consensus algorithm called Raft. Raft designs 3 states: follower, candidate, leader. Nodes normally stay followers. If they stop receiving heartbeats from the leader, they assume the leader has failed. Now, how does Raft election flow works? Here's what happens step by step. The leader sends heartbeats periodically. If a follower doesn't leave heartbeat within a timeout, it becomes a candidate. It increments its term number. It sends request vote messages to all other nodes. If it receives no votes from a majority, it becomes leader. That's it. Again, simple, deterministic, and majority driven. Now, why does majority matter? In a cluster of 5 nodes, we need at least 3 votes to win. Why majority? Because majority ensures there can be only one leader. If the network splits into groups of 2 and 3, only the group of 3 can form a majority. This prevents split brain automatically. But what if 2 nodes start elections at the same time? Raft solves this using randomized timeouts. Each node waits for a random election timeout. This makes it highly unlikely that 2 nodes start elections simultaneously. It dramatically reduces split votes. Now, we can also talk about the network partition scenario. Let's say we have 5 nodes. Now, the leader becomes isolated with 1 follower. That's only 2 nodes. The other 3 nodes form a majority. The majority group elects a new leader. The isolated leader can't form a majority, so it can't continue leading. When network heals, it steps down automatically. Split brain means 2 leaders exist at once. Raft prevents this using majority quorum, term numbers, and log consistency checks. If a node sees a higher term, it immediately steps down. This ensures safety above everything. Now, real systems which are using this is not theoretical. Kafka uses controller election, Elasticsearch elects master nodes, Kubernetes relies on etcd leadership, MongoDB elects primary nodes, Redis Sentinel performs failover elections. LeaderElection is everywhere in production systems. Now let's compare approaches. Random is unreliable, Bully better but not partition safe, ZooKeeper production ready, Raft modern industry standard. Today, almost all serious distributed systems rely on quorum-based consensus. So, leader election is fundamental to distributed systems. Without it, you will get chaos. With majority quorum, you will prevent split brain. With randomized timeout, you will avoid election collisions. And with consensus, you ensure safety. In the next video, we'll go deeper into Raft, not just leader election, but log replication, commit indices, and how consensus truly guarantees consistency. If you want to truly understand distributed systems, you can't skip consensus. See you in the next one.